Good morning, all. I'm hoping that you can all hear me now. We'd just like to welcome you to the Data Professional Technical Forum for April, for 27th of April, 28th of April. And we're here to talk about computer vision today. But before we start, I'm just going to provide an acknowledgement of country. I would like to respectfully acknowledge the traditional owners and custodians of country throughout Australia and the continuing connection to the land, waters, and community. I would like to pay my respect to them and their cultures and their elders past and present. Okay, so today we're going to talk about computer vision. This is a field of artificial intelligence that enables computers and systems to derive meaningful information from digital images, videos, other visual inputs, and take actions or make recommendations based on that information. Now today, 3 APS agencies will be presenting just some of the work that they are doing in this field. And some of the takeaways that I think you'll observe are that, one, computer vision is enabling a deeper extraction and analysis of unstructured data sets at unprecedented speed and scale. And these are data sets that we haven't traditionally been able to get as much value from in the past due to a lack of means to exploit them. Work in this area is reducing slow, mundane, and extremely labor-intensive tasks, lowering barriers to the use of image data. And over time, computer vision will become a ubiquitous capability in the public sector, as it is already increasingly in our day-to-day lives, enabled by industry and digital technologies. So the first presentation today, well, 3 presentations today are from the Department of Home Affairs, Geoscience Australia, and the Department of Agriculture, Water and the Environment.
Because essentially what we do is create an enormous big data repository of satellite observations and use that to understand what's happening with the Earth. The use of computer vision in Earth observation is normally done in the very high resolution part of the Earth observation spectrum, which is not something that Geoscience Australia uses very often, but is done for very specific purposes on a small scale. We tend to work at the national scale, so there are some slight differences there. Could you go to the next slide, please? Yes, that one. Thanks. So what we actually do, satellite imagery is not just pictures. It's actually measurements. It's measurements of the returning light from the Earth's surface to the satellite. On that particular journey of the light from the sun to the ground and back again, it gets distorted. And every image has to be fixed. It needs to be set up in such a way that if we want to analyze anywhere, anytime, throughout our entire archive, we have to provide a whole set of calibrations to make it work properly. And this is for things like atmosphere, it's the shape of the Earth, what's covering the Earth, such as forests or water bodies or whatever. All of these things change the way light is bounced around. And so we provide a set of corrections that normalizes all of this. So then we can look at one particular spot all the way through our time series, which goes all the way back to 1986, and then do the same sort of analysis over and over and over. Next slide, please. So here you can get a picture of the sort of imagery that we have to deal with. Clouds, because we use optical imagery, clouds are always in the way. And that means that it's very rare for us, especially this particular picture is from Hobart in Tasmania. It's very difficult for us to get clear imagery on some places like this. So we have a series of techniques that allow us to use the time series to actually build synthetic imagery. So this is not actually an image of what was seen. This is taking up an entire year's worth of imagery, putting it together and generating one picture, which then represents the median of all of those images. So this geometric median technique, it actually applies to all of the measurements that every single pixel represents on the ground. Now, a pixel represents the light of blue, green, red, near infrared, and the infrared part of the spectrum. And so when we do a geometric median, we're actually doing something like a 6-dimensional analysis, but we're also doing it through space and time. So it becomes something like a 9-dimensional analysis. In doing a median of this sort of thing, we use very strict mathematical techniques to ensure that what we end up with is a mathematically robust measurement. And that means that we can then use the same imagery, even though it's synthetic, in subsequent analysis and still get a proper representation of the Earth's surface. Next slide, please. This is a different version of how we would use the time series. So this is our water observations from space product. What we did here is we applied machine learning to our entire archive, and at the time it was something like 2 times 10 to the 13 measurements. And by having a look at that using machine learning, we actually detected the presence or absence of surface water for every single point in Australia from 1986 until the present day. And we continue this operation as an automated procedure. What this lets us do is actually understand the permanence of our water bodies, the differences between what is permanent and what is, for instance, flooding, and also to understand when changes happen in the environment, such as new dams or diversion structures in floodplains, or, for instance, when our salt lakes fill up. And so this gives us a very rich source of information from the aquatic side of the spectrum. Next slide, please. This is a similar idea. In this particular case, what we're doing is using machine learning to understand the separation within each observation. So we measure in roughly 30 meter by 30 meter pixels. So each one of those, we can break down those multidimensional measurements into just 3. And those 3 tell us basically how much vegetation is in every single pixel. So fractional cover, what it does is it says for every pixel, what is the percentage area within that of the green vegetation, the brown vegetation, and the bare soil. Now, this is a really critical piece of information. It was developed by the Joint Remote Sensing Research Program, which is a collaboration between the Queensland and New South Wales governments, and also the universities of New South Wales, University of Queensland, and others, and has provided probably the richest source of vegetation information for Australia. And it's now being also used in Africa. It's being used in Europe and other countries where they've decided that they're following on from our lead in how we're doing vegetation analysis. Next slide, please. This one is a slightly more esoteric use of the same sort of information. This time it's pushing straight into full artificial intelligence. In this particular case, what we do is we use the deep time series to create an understanding of what an urban surface looks like and also what urban change looks like. And so by doing this, we can create an ongoing view of how our cities are changing. In this particular case, we're looking at parts of Canberra, and we're seeing the separation between what's new development, what's old development, how much vegetation is in with the urban area, and how much is, for instance, very bare surface such as roads or concrete infrastructure and so on. Next slide, please. So it's all very well to have all these individual sort of snapshots of the different parts of our environment, and we have these great tools. What we try to do at every stage is to look at measurements rather than trying to infer information. So we don't try to just put a lot of information into a bucket, stir it around and say, okay, it looks more like this and less like that. What we really try to do is to directly measure everything that we can. However, as human beings, we like to be able to do that labeling, that classification. So what we then do, based on all the things I've showed you before and also other information that we have, is we start to combine them. And we have recently released a new product, which we call Land Cover. It's based on the United Nations Food and Agriculture Organization land cover classification system, and it brings together all these measurements to address that standard so that we can actually then look through time from 1986 to the present and show how the different parts of our landscape have changed and how they actually relate together in context. Next slide, please. So this is the structure of the LCCS. As you can see, it's somewhat esoteric, but the beauty of this particular structure is that it's very, very useful for anyone who's trying to do landscape measurement, because it just asks some basic questions and then provides attribution. So you can very quickly and very easily describe almost anything in our landscape at any scale. So what we do is we start off by saying, is it vegetated or not? Well, we apply the fractional cover method that I showed previously. Then we ask, is it aquatic or not? So we apply our water observation system. Then we ask, is it artificial or not? And that particular urban product is one of the contributors to that. So by doing this, we start to split things up into a set of classes, so labels, but which are derived directly from the measurements. So at each stage, should we find an error, should we find something that has gone in any way amiss, we can actually track back to where that particular error comes from. We can replace any part of this particular structure with a new and better algorithm. And that means that we have a truly robust and ongoing system which can continue to do land cover classification in the future. Once we have those first three sets of questions answered, so down to that artificial or not level, which we call level 3, we can then start to attribute what we're seeing. So for instance, let's say I have a vegetated area that is also terrestrial and natural. I can then start to say, all right, so what is the green vegetation cover? What is the height of my vegetation? What is the persistence? And all those sorts of questions, which then help to inform what is happening to our environment. And so that is what we've been putting out. Next slide, please. Unfortunately, as this is the PDF and not the animated version, I can't take you through this slide. But essentially, I wanted to show you how this breaks down across our various parts of the environment. But please ask me later if you'd like to know more. Next slide, please. So for this current release of our land cover system, those yellow bars that you can see there, they are the pieces of the puzzle that we have delivered so far. As I said, this is an ongoing product. It's going to be improved and updated in the years to come. We intend to add more and more to it. So for the moment, we are delivering vegetation that is both natural and cultivated. We're delivering the aquatic environment, which is vegetated and natural. And we're delivering the bare areas, so the non-vegetated terrestrial, both artificial and natural. So artificial gives you your urban areas, natural gives you your natural bare, such as bare rock. And then also the aquatic environment, we're not splitting that up into artificial or not, because from a satellite perspective, it's very difficult to detect the difference. However, in each of these cases, you can see that we've got various forms of attribution that we then are able to report on. And the importance of this, next slide, please. The importance of this is that this is a direct feeder into the United Nations system of environmental economic accounts, which is led by DOR and the APS. Recently, the experimental accounts have been released for feedback. That happened late last year, and shortly they will be officially released with our land cover as one of the inputs. At the moment, we have roughly 80 classes that we're able to report on. Next slide, please. Once again, I'd hope to give you some animation here. Actually, these particular images show a 33-year history of change in, for instance, how mining has changed the vegetation around for bauxite mining up in Weipa. The change in the filling and emptying of Lake George, and also in the top right there was bushfire impacts. I'm quite happy to share these animations if anybody's interested. Next slide, please. So this is not just about us providing data sets that are, essentially just dumb data sets that people take in at face value. We have a system of online access and interactive tools. This particular tool that I'm just giving you a quick snapshot here is what we call our DEA water bodies tool. What it allows you to do is to click on any water body in Australia and see the 33-year history of the percentage of surface area to its extent, its possible largest extent. And in that way, we can actually understand how much water is in our landscape. This has become a critical tool for understanding of the Murray-Darling Basin, of water in the hydro power regions of Tasmania, and several other areas. All of these tools actually are available online. If you go to the URL maps.dea.ga.gov.au, you'll be able to play with all of our data. You'll be able to have a look at any year. You can do comparison sliders, and you can have a look at this water bodies tool, for instance. Next slide, please. And I'm done for the moment. So happy to answer questions. I do have this particular presentation fully animated, and I'm quite happy to share it. Thanks.
Well, thank you very much, Norman. So we'll have questions after the last session. So please start putting them into the chat so they can be curated for that session. So moving on to our final presentation, we've got the Department of Agriculture, Water and the Environment. They'll be providing an overview of deep learning and image recognition, how deep learning image recognition is increasingly being used to support environmental recognition tasks, the key lessons learned, and further plans for the future operationalization of these types of capabilities. Andrew Jansen is an ecologist and data scientist supervising data science branch. And leads the department's artificial intelligence community of practice. Andrew's research focuses on applying artificial intelligence to environmental data to enhance decision making and to increase our environmental knowledge. So over to you, Andrew. Look forward to your presentation.
Thanks, Ron. Hoping you can all see my screen and hear me okay.
Well, looks good.
Sweet. Thanks. So yeah, my name is Andrew Jansen, and I'm an ecologist within the supervising scientist. That's within the Department of Environment. And I've got me here, but I just want to give a quick shout out to the massive team within the supervising scientist and Microsoft, our collaborators who have been working on all our different projects. So I wanted to just start off by giving you a bit of an overview of the supervising scientist and sort of the drivers behind why we were venturing into deep learning and computer vision, share some lessons that we've learned, and then where we're actually taking that work. So, like I said, I'm from the supervising scientist. We've been around for over 40 years now. I'm from an environmental research institute within it. So it's based in Darwin, and we've got a field station out in Kakadu National Park. And essentially, our function is to protect the Alligator Rivers region from the potential effects of uranium mining in the region. So a lot of our work is focused around Ranger Uranium Mine, which is surrounded by Kakadu National Park. And that's because of the high cultural and ecological values of the area. So you can see the mine here, and it's moving into a restoration stage where it's going to be filled in and incorporated back into the surrounding area. So one of our monitoring programs where this all started is around our aquatic ecosystem monitoring. So around the mine, there's freshwater creeks that are seasonal. So it's a wet and dry season. So we've got seasonal streams that flow downstream into rivers and then the wider floodplain system. So they only flow during the wet season, and then we do a lot of our monitoring during the end of the wet recessional flow period. So I'm going to focus on our fish community monitoring. So we monitor fish assemblages up and downstream of the mine in both channel and shallow lowland billabongs. So traditionally, in channel billabongs, so they're the deeper habitats, we would have our field teams out during that monitoring period, and they would survey fish populations in this pristine, clear water by somebody laying down in a boat. So you can see in a bubble boat there with a paddler, and they would count fish and yell out what they see to somebody else in another boat, and record the assemblage, and hit different transects and different billabongs. And then we would also monitor shallow lowland billabongs. So these are, as the name suggests, shallower, full of aquatic vegetation. So we would use pop nets, as you can see in the picture here. We would actually go out and push the pop nets into the vegetation and then trigger them, and then pull out all the fish and the vegetation, identify it to species, and weigh it all to get biomass and the full quantitative data set. And essentially, these were going on. We have some of the largest longitudinal data sets on these habitats in the NT. But essentially, we had to look at different ways of doing this monitoring due to increased crocodile risk in the NT. So it was no longer safe to send people out into these water bodies. What we did was what everybody else is sort of doing in the fisheries monitoring, and particularly in the marine space, is we used underwater videography. So putting GoPros or any underwater cameras onto stands in both of those habitats. We'd put benthic ones and surface ones to get the different fish assemblages. And then we started collecting about 300 hours of videography per year. So that really represented a shift in data that we had, where before we had field teams out collecting data, spending a lot of time out in the field, and then come back with their data sheets. Where we gained a lot of efficiency in that fieldwork respect. Now we have people sitting at laptops, going through hundreds of hours of video, identifying fish. So after seeing an NT Fisheries and Microsoft collaboration on how they're using computer vision, we thought, oh, great, this is going to help us. So we sort of launched our BravNet project, which is AI for fish. So in order to do that, to use computer vision, we need to get a training data set for our local fish species. And because there isn't a training data set for all our 30 to 40 freshwater fish species that we encounter, we had to develop our own. So essentially what that is getting pictures of fish, annotating and labeling it, training a neural network with all that variation that we'd expect, and then using that model to predict new imagery and get it to automate the fish species identification. So if we look at some of our imagery here, you can see fish move in three-dimensional space. The imagery is quite complex. You have different morphologies, color, lighting, because of the different depths. You have lots of schools of small fish like that, which presents a challenge when trying to get a training data set, because you need to capture all that variation of how the fish moves in 3D with the background and lighting to try and get a confident prediction from a model, including all those species. So because our imagery, a lot of the complex one would have fish overlapping, we looked at using instant segmentation to segment the fish and get an accurate abundance measure from this type of data. So that's where we put a polygon around each picture of the fish, like you can see here, and apply a species tag. And so you can imagine if you're looking at 30 to 40 species and needing to capture all that variation, we need a really big data set, which was going to take time, and there's limited resources. So we took a citizen science approach to that. So it sort of had two parts to it, where we had an image labeling challenge where we put our imagery out to the public, and people could request a data set and put the polygons around the fish for us. They didn't necessarily have to know the species tag. And then once they were all labeled, then we'd have a fish ecologist go in and just do a quick quality control check, apply the species tag if needed, and then combine it with a master data set and really keep that growing. So we have a website, you can go to check it out. It's bravnet.org. And during the project, we sort of learned a lot about how to label, what is a meaningful label, what information do you need to give the model for it to, be confident in a prediction. So we incorporated all that information so people get guidelines on how to label fish, and then some of the taxonomy information of what we're trying to do so they can learn the fish species as well. So once we got a training data set that for all our representative fish species, we then want to use it. So go into a new field season, come back with our hundreds of hours of videos, and then use that model to predict all the fish. And essentially what that looked like was, we're coming back with over 500,000 frames that need to be predicted against a model, and trying to do that on a normal laptop would take months. So where we've gotten to, and what our aim was to be able to come back with a folder, so video 1, 2, 3, 4, all the way up to 300, and then put that video on a VM with the model and get it to predict every second of footage. So every second of footage is getting information about it and writing it out to a database or a CSV. And then for every image that has a positive prediction, it saves a picture of that, so we can then go in and check to see what it is predicting and understand what it's predicting wrong and right, and then build our training data set that way. And then we used Azure Batch to be able to, okay, we can put one video up on a VM, but then we can, in parallel, put up, video 2 at the same time, or go put 300 VMs at the same time and have it all run in one day to really be able to handle the volume of data. So hopefully this video works. This is just a video of one of our model in action, predicting fish live in video, and you can see it's the polygons are pretty tight around, and the species is pretty high confidence as well. So we're happy with how it's progressing. And then just to sort of summarize the high-level architecture of that fish project, we're collecting data. We need to set some guidelines around how to annotate and label it so that it's actually meaningful information that a model can use and is of a high standard. And then we found, after all of this, all the value and time and money is in this data set, especially for environmental or ecological applications. If you're trying to apply it to a local region, you need local specific data. And at the moment, there's a bit of a limitation in publicly available data for that. So once you've got that data set, sky's the limit. You can use it in research, commercial, do more competitions, and then have some pipelines that can just pull that data set and start, retraining and using it in any different way. So I guess I'll just pause here just quickly to say that if anybody is working on similar problems or has data sets, please reach out, because we're always looking to build it, because it is very time intensive. So once we finished with the fish, or we sort of learnt that problem, you recall that I said that we were measuring vegetation as well. So because we weren't putting people into the water, we had to come up with a way to map the vegetation community so we can derive that fish habitat relationship. So what we moved to is using drones and multispectral imagery. So the reason we're using drones is because we are in a tropical area with lots of cloud cover. If you fly a drone, we can sort of get around cloud cover issues with satellite imagery and get data for the day and time that we actually did the field operations. So using drones with a red, green, blue, but then also multi-band imagery, so adding the near infrared and the red edge bands, we can do spectral thresholding, as was seen in the previous presentation, to derive the vegetation, and then look at how we can then apply deep learning to it. So if you look here, this is one of our billabongs. You can see when you zoom in, you can see everything. You see the emergent vegetation, lilies, even submerged vegetation, particularly with those extra bands. You can start to pull out submerged vegetation from the water. So using the traditional methods of a manual way of classifying the vegetation, we can do it for the whole site, which is, again, an increase in the data compared to the previous way that we were measuring vegetation, because now we're getting vegetation metrics at the scale of the whole billabong. And then if we take the GPS coordinates of the cameras that we put in for fish, we can take a little buffer around and extract the vegetation assemblage and relate it to the fish for every individual camera. So getting that really comparable information. And yeah, there's just a couple of categories that we're classifying so far, and hoping to move down into species level. So because we've got those maps classified that manual way, it's essentially a training data set, so we can train a model and then get new billabong imagery. So we're going to a different site, pass that new billabong through the model and get it to predict the vegetation assemblage. And we still need to get more training data for this, but we want to get to that stage where we can just fly a billabong and have it spit out a vegetation map, which would be great. So I'll just finish up by touching on how we've expanded what we did with the fish and this vegetation mapping into other use cases, and after, you know, all the learnings out of that. So from a biosecurity context, they also deal with fish. So 100% of live fish that are imported into Australia are required to be inspected on arrival. So once they arrive in these boxes, fishing bags are inspected by a biosecurity officer. There's over 250 marine and freshwater fish species, and you can see here permitted and non-permitted species can look really similar. So training officers is very time consuming, and non-compliance can be accidental or deliberate. So what we're trying to do here is pick up our fish model and data set, because there's still a lot of value in that. We have a model that if we just pull the species information, that it can actually identify a fish, and then we can fine tune it on all these fish species that are imported for a completely different use case and require less training data with that transfer learning. And then the end game is to have these models surface in a mobile phone app that an officer can then use as a support tool to be able to be really confident in their identifications. And then one of the other areas that we're pushing into is, if we look at billabongs in Kakadu, and we push further out into the savanna woodlands, part of the other monitoring and research program supervising scientist does is we're characterising that surrounding woodland vegetation to inform the restoration of the range uranium mine site. So when they cap it and replant over the mine site, having that information to say, this is what the surrounding environment looks like, this is what the restored mine site should look like. So this is a bit of a bigger challenge, flying drones and long-range drones to map hectares of the woodlands, and you can see it's really patchy and variable, and tree species, when looking at from above, lose some of that taxonomic identification features that you would normally see from a ground that a botanist would use. So we're going out and generating a training data set using ground surveys to validate what we're labeling in the aerial imagery, and then again training neural networks to classify trees from drone imagery, and making good headway with that. And then just to a couple of the other quick ones that I haven't got slides for here is where training models for camera trap imagery and to identify birds in acoustic sensors. And I'll leave it there. Oh yeah, sorry, and there's some resources. We have the code developed for our fish project in a GitHub repository, and yeah, please reach out if you've got any data sets that you'd like to share or access. Thanks.
All right. Well, thank you very much, Andrew. That was fascinating. I really love the crowdsourcing and getting the public involved to help label data sets, and I'm very envious of your ability to do that. So we have a few questions now, and continue to put your questions through. So I'll start with, and I know that some of the presenters have been answering some of the questions in the chat, so I will still read them out just for the benefit of anyone who's not looking at the chat window during the presentations. So there was a question about image formats for home affairs, which Fraser did answer in chat to one of the audience. I just would make an additional comments on the image formats, and to say that the Department of Home Affairs is a very diverse, very disparate organisation, and very large organisation, and we often don't have control, or a lot of those formats were decided years ago, and we kind of have to work with what we have. So we do tend, we certainly want to make recommendations for better for specific standards for image, and that will be very important in the future. But at the moment, a lot of the image formats are chosen by their ease of implementation. So PDFs, for example, for documents as a standard tool that everyone has access to, and that we get those from our clients and from visa applicants through those means. So we don't have the ability to control what formats necessarily come in a lot of cases. So that's just an additional comment to the back and forth I saw through the chat there. So next question is for Norman, which I know you did answer in the chat, but for the benefit of everyone else, could you please answer that again? And that was, how important is base level geography, i.e. the grid system, in the formation of the products that you produce?
It's not particularly important. It's actually more important to make sure that you do as few transforms as possible from the base to your output product so that you don't introduce extra errors. All geographic transformations are non-reversible, not perfectly. So there's always an error. So when we get the imagery from, for instance, Landsat comes to you from the United States, it comes to us as a UTM, so Universal Transverse Mercator projection at roughly 30-meter resolution. And we keep that until we create derivative products. So we try to make sure that most of our analyses are done on the raw grid standard. And then when we try to do a national product, we then transform at the end to an Albus equal area. And that allows us to do, as best we can, national area comparisons of environmental features.
Cool, thank you. So I've got a question for Andrew, and that is, what size training data set did you need for the effective fish species model, or what size do you think you need, and what were you able to build with the help of the public?
Yeah, so we're actually still going through all the citizen science images because we did get a lot of uptake. So we're still getting, we'll have to wait for final numbers on that, sorry. But one of the data sets we have that we're using or testing for monitoring is we've got about 45,000 images that have been labeled that relate to about, I think it's around 130,000 actual annotations with 2 species level, which is, yeah, massive. And we're getting around 80% mean average precision on that model. So we're collecting temporal data over a few years to see if that sort of result can still capture the temporal variability in fish assemblages, and then just incorporating new data every year because it's hard to get.
Okay. I've got a question for Home Affairs, which I'll take, which is, are there any privacy issues associated with your computer vision pilots? If yes, how have you addressed those? Now, I would say that the department does take privacy very seriously, and our data division is responsible for privacy. All of our staff are trained, do mandatory training on privacy training. And we are 100% fully compliant. So we have a range of measures that we apply, things such as not emailing data sets, using trim, which there's a bit of discussion on the chat I saw, and our official document of record, and providing a link so that we minimize the risk of any leak of data or any privacy breaches. But most of our work at the moment doesn't have any major privacy risk at the moment, but that's certainly something we're mindful of in the future. So I have a question for all panelists, and I'll read this out. So Norman mentioned the use of international standards vegetation classification. Is there much collaboration internationally around techniques mentioned by the other speakers? Machine learning for environmental monitoring or male scanning comparisons. So I'll throw over to Andrew from DOR for that question first, and then I'll go to Fraser afterwards. So over to you, Andrew.
Yeah, so I guess from our experience, we're collaborating with anyone who will. So mainly we're working with Microsoft, who have really helped us upskill. But we're talking to universities. There's lots of pockets all over Australia working, I think, in isolation on a lot of these things, and they're actually sitting on some pretty good training data sets that would be great if they could be leveraged into the public. I would say for environmental data, there could be more sharing and collaboration.
Cool. Fraser, would you like to answer regarding the mail scanning comparisons?
Yeah, so for international mail, Home Affairs works with our Border 5 partner agencies on analytics problems. So that's USA, Canada, Britain, New Zealand, and us. So we have regular interactions and communications around these problems, and we know that the stuff we're solving is directly applicable to those overseas agencies as well. So that's at a computer vision level. There's expertise sharing going on. With mail itself, there are international standards around mail, and ideally, we wouldn't even have to do computer vision on this on this problem. We would use the advanced electronic data that some overseas countries provide us with to get this information, and that's an international standard managed through the UPU. But unfortunately, not all countries adhere to it, and not all countries are capable of adhering to it. So we have this necessity to process mail items this way. And I guess the final standardization point I'd make would just be around the labels themselves. There are standards for customs labels used internationally, but unfortunately, even those standards have many, many variations, and they're not enforced in a mandatory fashion. So even though we might have 20 or 30 different types of labels typically coming through, there could be many hundreds of variations of those that we have to cater for. So it makes our life a little more difficult than it otherwise would be.
I'd add to that with regards to our partners, and don't forget the Dutch, Fraser. We are working to do much more collaboration in the space, so that threats that our US colleagues see, if we share models and we share data and we work collaboratively with them, we can be protected by the threats that they see first, and they can be protected from the threats that we see first. So there's very much a strong incentive for future data sharing and collaboration, and with that obviously goes developing common approaches, standards, and getting the engineering right, as well as hopefully getting a bit of crowdsourcing of our data labeling, because that's obviously that's a very big challenge for us. And in the past, we have had one poor person, spend 6 weeks doing mundane task of labeling data. But very, very envious again, Andrew, of your crowdsourcing methods. I have another question for Norman. So Norman, are you still able to estimate biomass of the vegetation using imagery? Not sure if you answered that in chat already, but I'll put that out there.
That's okay. I did put a note into the chat. There's some new work. It's just been released from the European Space Agency, their CCI biomass program, which has a lot of our collaborators involved with it as well. And essentially what they found was that you can generate a reasonable biomass estimate of vegetation if you can get good measurements of height and cover. And so they've actually been able to produce that at the global scale, and they've done a couple of years worth. This is an ongoing area of research though, because we really do want to get better ideas of biomass, both above and below ground. And also we want to be able to get to carbon above and below ground, and blue carbon. So a lot of good work going on there.
Cool. I have another question for our male colleagues. So I think, Fraser, this is you. Are you using AI-based object shape capability to identify potential features or contents in mail?
Yeah, I didn't go into the sorts of objects we detect within an image, but I guess the answer is yes. So we look at the package itself, we look at the stamps, the label, the nature of the package, any special markings, a bunch of other features as well. And so we use object detection methods to extract that information. And when we're doing matching, we can use that to enhance the match between packages. It's the same, the officers that are doing this task manually right now, They do a similar process where they look for those key features that describe a package. So we're trying to replicate some of their expertise through automation.
Okay. Norman, I have another question for you. Do we have enough AI training material to start identifying large veg species or species areas from high-res satellite imagery, both invasive and non-invasive?
So my answer to this one is not really. We actually lack good databases, especially at the national scale, which can really give this sort of information. I know of some small studies, so areas where they can really constrain how far they're going and how many different species are in there to be able to do this sort of thing, but it's not readily transferable. So yeah, a lot of work needs to still be done there.
Cool. I have a question for Andrew. Have you had to evolve your approach to data collection due to cost concerns? Perhaps limits what you originally had planned. Just to make sure you fit it inside your budget.
Not really. I think the cost savings we would have, like for an example, our fish monitoring fieldwork, we would have to send a team of 15 people out for 3 weeks to go and survey those shallow lowland billabongs. Now we can do it in 6 days with 2 to 3 people. So the savings we save in man hours out in the field, we can put into cloud compute or data storage. So yeah, we haven't looked too close at it, but the efficiency gains from using the new tech can be made up elsewhere.
Cool. Now, I think I'm out of questions, Kirsten, unless any others have come through.
No, not that I can see.
So I'll put out a last call for any questions. If you have any, furiously type away. Otherwise, I think we may conclude. All right. All right. Well, we're actually 10 minutes ahead of time, which is. Oh, sorry. Far away. Someone speaking. All right. No.
I think we're good.
We're good. All right. Well, we might conclude there. So please thank all of the presenters today for all of their hard work and their generosity in sharing their current journeys. I know I'll certainly be looking to have a look at Lake George and how it's filled up over the years. It's always an area of fascination for me. I definitely, Norman will definitely appreciate seeing those animations. Kirsten, I might throw over to you if you're going to talk about where the presentations will be hosted for those that will be shared. My apologies, the Department of Home Affairs presentations weren't recorded today and won't be shared just for sensitivity reasons. But I believe the others are recorded and will be shared and hosted through the usual channels.
That's correct. So Andrew's and Norman's presentations were recorded and they will be shared through the APSC website in the coming weeks. So they will be available for viewing.
And I'm hoping that includes the fully animated version of Norman's presentation as well. But
yes, we'll make that available. My apologies for that, Norman.
Cool. All right. Well, feel free to put a applause or clap in the chat, or sorry, or use the emoticons, and I think we'll wrap up there. And thank you very much for attending this this forum. I hope that you all learned a great deal of some of the great work that's going on within the APS. So thank you very much, and a special thank you to all of the presenters today from me. Thank you.